Okay, so we went through the idealized tide predictions and looked at how the unequal tides are generated based on where you are because of the declination of the moon, right? The northern hemisphere, southern hemisphere are a phasing of the higher high tide and lower high tide, and how the tidal heights differ based on the latitude, etc. Now let's look at the real tides. Real tides means now we don't have the aquaplanet anymore. We let the continents come up out of the water and see what will this do as the tidal forces are trying to drag the ocean around and the ocean hits the boundaries. Why? Because we have been talking about the ports, the tidal charts and so on, all without adding the coast. Now we're going to add the coast. As soon as you add continents, the tides, remember tides are shallow water waves, which means they are going to feel the bottom all the time, which means bottom friction is important. Okay? And they modify tidal bulges. Okay? So continents are going to matter, and friction with the seafloor is going to matter. And the idealized tidal bulges cannot form anymore because you don't have this nice aquaplanet anymore. So the bulges that are supposed to move with the moon cannot keep up with the Earth's rotation anymore. We had said we have nice bulges and Earth is rotating through them in the aquaplanet, but here that's not the case anymore. So you're going to end up with crests and troughs of tides rotating around what is called an amphidromic point. That's the point that has very low tides. It basically no tidal range at the amphidromic points. Okay, and it involves CoTidal lines, which means from the amphidromic points you get the same tidal range along lines going out from the amphidromic point to the coasts. And those CoTidal lines rotate, and the direction of rotation depends on the hemisphere, as always, right? So the tidal waves rotate once in 12 hours because we still are stuck to the diurnal cycle, because the moon earth system is still doing their rotational things. And this is how the CoTidal map looks. So gone are the nice bulges and the higher high tide and the lower low tide and so on and so forth. So here is an amphidromic point in the northern hemisphere. Here one that is very close to the equator. Another one this is south of the equator, and so on and so forth. North of the equator here, north, etc. So using this clear one here and these, you can see that the numbers on these CoTidal lines, the tidal range along these lines is the same. That's why they're called CoTidal lines. And you can see that this CoTidal line is moving from this amphidromic point to this amphidromic point. Obviously, it doesn't make sense anymore from the point of the idealized tides we've been talking about so far. The numbers here are the hours. So 0 is the hour that the CoTidal line is starting here. After 2 hours, it's here. After 4 hours, it's here. 6, 8, 10, and back to 12 or 0 again. So that's a 12-hour cycle, right? So here is again 2, 4, 6, 8, 10, 12, and then it's complicated by this other amphidromic point and so on. You can see the tides going up here and so on and so forth, right? So this CoTidal line is also coming out of this. So they're crossing the equator. Because they're shallow water waves, they can just go wherever they want. They move pretty fast, right? Square root GD, remember, and D is several kilometers deep. So you can imagine how fast the tides can move, just like tsunamis. Tsunamis move at several hundred kilometers per hour. But anyway, so the main thing to note here is that the CoTidal lines rotate in a counterclockwise in the northern hemisphere, just like a cyclone, and they rotate in a clockwise direction in the southern hemisphere. Counterclockwise direction in the northern hemisphere, clockwise direction in the southern hemisphere. Sorry. Okay, so life gets complicated as soon as you add the continents. Tides break up into CoTidal lines and amphidromic points. They cannot keep up with the Earth's rotation anymore, and they hit the coasts at various time scales. So here is a animation of the rotation of the tides, and you can see it's not even as clean as we showed before, but you can imagine there is a minimum tidal range here, and then there is a counterclockwise rotation here, and there should be a clockwise rotation here if you can see it clearly. Okay, so in other words, as soon as you go to the real world, the tidal problem is not so simple anymore. So predicting tides is not that simple anymore. This is what it means when we say there are 400 factors that determine the tides in the real world, right? So life is not simple, but nonetheless, tidal prediction is now very solid. They are being improved all the time because, as I said, we need to subtract the sea level oscillations because of tides to extract the small changes that happen in sea level because of global warming. That's the ultimate goal of these satellites, to track sea level rise, and the sea level rise happens at 3 to 5, 10 millimeters per year, very tiny. A satellite sitting at 1400 kilometers is measuring it very accurately. That's pretty amazing, right?